Hello everyone, welcome back to another video for the series. I'm Inakyu and today I brought a very fun and interesting problem from the IMO, I think 2023 IMO. Uh, to be honest, it's been a while since I studied this problem, so please forgive me if I get stuck. Also, I remember reading three different solutions for this one. I think one using Pascal, the other one using cross ratios, and the last one using similar triangles, but the setup to use Pascal's theorem and the cross ratios were quite difficult. So if my memory serves me right, I'm planning to use um, the solution using similar triangles. So let's start by drawing the diagram first. Let ABC be an acute angle triangle with AB less than AC. So something like this. Um, yeah, I think this is a great triangle. Triangle A B C. Let big omega be the second circle of triangle ABC. So uh, almost there. Nope, only the circle. No. What? I think this is a pretty good circle. Um, yeah, perfect. Let S be the midpoint of arc CB containing A. So this point is S. A perpendicular from A to BC meets BS at D and meets big omega again at E not A. So a perpendicular from A to BC like this meets BS meets BS at D and big omega again at E not A. So this point is D and that is E. The line through D parallel to BC meets BE at L. So one more line, going like this. Yeah, and BE, like EB from here to there. Oops. So that is L. Yes. Denote the circumcircle of triangle ABC, I mean BDL, by small omega. So that BDL by small omega. Let small omega meet big omega again and P not B. Prove that the line tangent to, so that point is P. Prove that the line tangent to omega at P, small omega at P, meets BS. So like this, they look tangent. At B, and BS mean at the internal bisector, angle bisector of BAC. So from here to here, like this. Okay, cool. So from here, I think we can write the information that we know. First of all, this is the midpoint of arc BC not containing A. Because this is the angle bisector, this and this, they have this chord and this chord have the same length. So A, B, C, D, E, F. So BF equals FC because this is an angle bisector, meaning this is the midpoint. So if you connect from here to here, right angle, this is the midpoint. Here to here is right angle and midpoints, meaning a line connecting from here to here, here to the midpoint and midpoint here is a straight line. So yeah, this is the straight line and they are tangent, perpendicular to each other. Meaning AE and SF are parallel. So this is one thing that we know. AE is parallel to SF. We know that they are parallel to each other. Alright, so we connected from the midpoint to the midpoint. Oops. Meaning SF is the diameter. Yeah, because we connected it from midpoint to midpoint, and SB, FC are cyclic, while angle SBF equals angle SCF. So, so it must be the diameter. So SF is the diameter. Okay. What we want to do right now is we want to prove that there exists a point that lies on all three lines AF, BS, and P something. A, B, C, D, E, F, G. Let's call this G. And therefore, if we prove that, okay, let's just say that PG, let's just say that H is defined as the intersection of two red lines, so AF and PG. That way, if we prove that H lies on BS, then we're done. Because if H lies on BS, then that means H lies on all three lines, and it also tells that they are concurrent. Those three lines are concurrent. And prove that the line tangent to omega IP meets line BS on the internal bisector of angle BAC means that those three lines prove that those three lines are how do you say that? Concurrent. So we know that SF and AE are parallel to each other. Then I think we also know that AH. No. Instead of PG, let's change to BS. I think that would be easier. So BS. Then we know that triangle AHD. So notice the triangle AHD is similar to triangle FHS. Are they? Yeah. Yeah. We want to somehow use this fact. And I think using this explicitly would be difficult because, looking at this triangle, they don't give us any more information. So why don't we try and use these ratios? Maybe using ratios will help. So using that ratios implicitly would be drawing another, I'll say, triangles, similar triangles, perhaps. One more from here to here. Notice that this is a right angle. Using this and that, this and that, maybe APD, triangle APD, because that's the only plausible triangle that we could see right now. Other ones don't really make sense. But if this explanation doesn't seem good, just we can say we think we can see triangle PAD right away. Yeah, I think it's quite obvious to see triangle APD. But there might be other triangles using those two ratios, but it's most likely that we have to use triangle APD. Let's start tracing our angles. Okay, so if they are similar to each other, they look similar to each other, and if they are similar to each other, we could use all our other ratios, and that could help us prove that H actually lies on PG, because we are allowed to use P something to something G if they are similar. Because this H would be the center of homothety or center of perspectivity. So let's chase our angles. I think it would be really important to choose a good angle. A good angle by here means something like this. LDB, because we know that they are already parallel to each other, so they are equal to that. Like this. And SBC, so it's saying it's equal to SFC, SEC, SAC, but I'm not sure if it will help. Because this is 90 degrees, we know that this is 90 minus blue. Oh, why don't we, yeah, we have 90 minus blue, and 90 minus blue seems like a good angle. Because if we actually, let's take a look at this one. APBE, points APBE, and PLBD. Because general rule of thumb, if you have a point, if you have multiple points on a circle, we could use 1, 2, 3, 1, 2, 3, 4, 5. We could use Briantian's theorem, or like cyclic quadrilateral. Wait, maybe we could use Briantian's theorem, maybe. But it's really unlikely. Wait, what? Really? We can use that? 1, 2. Wait, really? I'm not sure because I don't think the solution. Yeah, I actually forgot how Briantian's theorem went. 3, 4, 5, 6. No, instead of E, let's use S. Because we will not use S here. A, P, B, F, G, S. A, P, B, F. A, P, A, P, B, F, G, S. 1, 2, 3, 4, 5, 6. This one. This one. Whoa, wait. No way. No way. Actually, no way. No way. We are done, actually. We are done. Yeah, we are done. Nope. What am I saying? We're not done. We're not done. Eh? Never. I'm so sorry. Yeah, we're not done. Because it doesn't make sense for a problem to be this easy. Hmm? No, maybe. Wait. No, if this works, then no, this shouldn't work because. Oh wait. No. No, because Pascal's theorem is about um collinearity. No, but I remember Pascal's theorem relating to concurrency too. No, maybe I was confused. Sorry, yeah. Yeah. No, nope. Yeah, never mind. I'm sorry. Doesn't work. Because, yeah, it doesn't work. Okay, then let's start chasing our angle to see if it will help us. Okay, so general rule of thumb, if we see multiple points on a circle, we could use cyclic quadrilateral. So this equals this angle plus that angle. This angle plus this angle equals 180 minus that angle, but 180 minus this is equal to this angle. So this and that, they are equal to each other. This and that, they are equal to each other. So this plus, oh, okay. So angle PAD equals 180 minus angle PBE. And this equals PBL. And angle PBL equals angle PDL. So angle PDL plus angle APD equals 90 degrees because this is parallel to this line and this is a line perpendicular, meaning what is PDL is angle PAD plus angle PAPD equals 90 degrees. So this angle plus this equals 90 degrees, meaning this angle is right angle. Nice, nice, nice. I think the next one that we can try is trying to prove that this they're all three pairs of sides of corresponding sides. Yes, I found the right word. So if we prove that all three triples of corresponding sides are parallel to each other, no, actually, if we prove that all corresponding sides are parallel to each other, then we're actually done because that means H will be the center of homothency of triangle APD and triangle FGS. So we just need to prove that this angle equals that angle, or this angle equals that angle that way, because we know that they're already parallel, this and that, yeah. So if we prove that these two triangles are similar, we prove that all of those corresponding sides are parallel to each other, and that tells us that H is the center of homothency. I'll get more into center of homothency thing because, yeah, there is a little more thing to talk about there. So let's prove that they are similar first. Or we could just prove that if AP and FG are parallel to each other, then we're done. So we either need to prove that these two triangles are similar, or at least one more pair of corresponding sides are parallel. So let's take a look at equals that. Yeah, how about we take a look at this angle, because I think it will be easier to prove that this angle equals that angle, because other ones you can't really find a good pair. If it doesn't work, then we could move on to another one. So yeah. So if this is green, we could use that Oh, nice, nice, nice. That's really nice. So this one is also green then. Yeah, the reason why this one is green is because PG is tangent to the circle. So, um, yeah, because if this is tangent, this angle and that angle are equal to each other. Because, yeah, I mean, this is the property that I think I mentioned multiple times, and also it's quite basic property that I think we all should know. So I'm just gonna skip the proof. It's really easy to prove it. Just use no, I'll just prove it again. So let's say this is alpha, this is 2 alpha perpendicular, and this is 90 minus alpha, so this is alpha. So we just use that property. Okay, if this is green, this plus that is 180. Hmm. Oh, wow, wow, wow. Nice. Let's take a look at angle PBS, PGS. This is green. Boom, they're parallel. Okay, nice. So we know that PD is parallel to SG. Therefore, this angle equals that angle, but we already know that these two are the same because they're parallel. So angle PDA equals angle SFG, meaning those two triangles are similar to each other. Therefore, triangle APD similar to triangle APD FGS. Okay, we know that they are similar to each other and all their corresponding sides are parallel. Then I think we could write a few information from here. So AF BS is H. So we know that B BS no DTS. What is this? We know that AD to SF equals AD to SF equals DH to HS. But let's call another point A, B, C, D, E, F, G, H, I as the intersection of PAAF and PG. So this is also equal to AD to SF. AD to SF equals AD to SF equals let's use PD to SG. And notice that PD to SG equals AFPG. No, actually, let's use the other one. Sorry. This is equal to AD to SF equals PAP to GF. This is equal to AI to IF. So DH to HS equals AI to IF. What is AI to IF? That's obvious. AI to IF. AI to IF. Oh, that's equal to DI to IS, right? Because if we take a look at, because AI to IF equals, so we're going to take a look at these two triangles. AI to IF, then no, we can't do that. We cannot do that because we don't know if I actually lies on DS. Wait, I'm sorry, we don't have to do that. We don't have to do all this. We don't have to do all this. We could actually use different explanation. Yeah, I was just trying to use my basic approach because I think I also tried that method on my own. But okay, if two triangles are similar to each other and all their sides are parallel, all their corresponding sides are parallel, then we know that that triangles are in homotety. Yeah, so if we actually, so all similar triangles are the image of homotety of the other ones, other similar triangle. That means there exists a point of the center of homotety, and that's this point right here. The intersection, let's call that, sorry, let's call the center of homotety as H. So therefore, H is the center of homotety. Because let's think of it like this: AF and BS, right? Yeah. So let's think of it like this. With H being the center, this to that equals this to that equals that to that. That's how we how we I would say how do you call that? How we expand it. Yeah, that's how we expand it. So we know that there exists a point of homotety. I mean the center of homotety. There exists a center of homotety, and in this case, this is actually equal to the center of perspectivity. They're actually both center of homotety and also center of perspectivity, because there exists a point such that um, um, yeah, such that it gives the same ratios, and that is the intersection of two lines, and we just call that AF and BS, and therefore H also lies on PG, because PD to DG is also equal to AD to DF, and also DH to HS. So because center of homotety or center of perspectivity all meets at a single point right here, yeah, we could say that all those three lines are concurrent, and we've concluded our proof. So when I first studied this solution, I think I'm not sure if it's entirely the same. I'm not sure, but it was something similar to this one or the same. I was trying to use Desargues' theorem because Desargues' theorem utilizes the center of perspectivity and the axis of perspectivity. However, notice that these lines all meet at the point at infinity. So I actually couldn't use it. So, I mean, I think we can use that, but like I'm not like that advanced. So, yeah, not that advanced in using Desargues' theorem. So I wasn't able to use that. But I do remember using the explanation that I was trying to do. So let's say that, yeah, let's try that one again because I think that also worked. AD to AF and PG. AD to SF equals AH to HF, but AD to but AD to SF is AP to GF. This is AP to GF is equal to AI to IF, obviously. Therefore, H and I are congruent to each other. So AF and PG equals AF and BS. Yeah, so the union of, no, not the union, AF cap BG. So the point where AF and PG meet and where AF and BS meets are the same. Meaning all those 3 points meet at, all those 3 lines meets at a single point. So they are all collinear. I mean, they are concurrent. So that also completes our proof without using like homotety and perspectivity stops. So using simple ratios and similar triangles. Yeah, so I think that's about it for this video. I'm not sure, but I think this video will be a super long one. It took me a while to draw the diagram and do the stops. So thank you so much for watching this long video. Tomorrow I'll come back with another very fun and interesting problem. Thank you and see you tomorrow. Bye.